All right, we got done talking about part of oblique triangle trig when we were doing the law of sines. The previous video was about the law of sines. So, what can we do with the law of sines? Well, if we have a triangle where we have any two angles and one side length, we can use the law of sines. And the reason for that is because if we have two angles inside of a triangle, we have three. Because all the angles, all the degrees, all the angles inside of a triangle add up to 180 degrees, which means that this one here would be what would this be? It'd be a 90-degree angle. And we can use that information to find the rest of it. This would be a right triangle. If I had instead given you a different angle, like let's say this was 40 degrees also, then that means this would be 100 degrees. And now we can set up some ratios here. We can say, for example, if we wanted to know this side over here, remember that's 100, not 900, then we would say, all right, so 5 is to the sine of 40 degrees as x is to the sine of 100 degrees. And we could do this and we'd solve for x and we get the answer. Um, and it's great. The law of sines is very versatile and you can even use it in some very, very complicated type questions, which we'll get into in a later video. However, if we don't have the correct information for the law of sines, meaning essentially that we're unable to set up a ratio, then what do we do? And this occurs generally when we have we can't if we have three sides and if we have just all three sides we don't have an angle to set up, so we can't have a ratio of a side length and the sine of an angle, so we can't do that. And in a situation where we have two sides and an angle, we also can't just straight away use the law of sines. Now, it's possible. Depending what angle you're given, it's possible to use the law of sines in those situations. But in this specific situation here where we have the side, angle, side, remember we read these kind of clockwise. So we would say we have a side, angle, and a side. That's like the poster child for using this other method called the law of cosines. Now, the law of cosines is kind of intimidating, but it doesn't use any new ideas really that we haven't already discussed, either using just purely right angle trig or in the process of deriving the law of sines. So this is kind of how that works. If you, again, this is just a standard oblique triangle. If we drop an altitude from any of the vertices and call that something, in this case h, and then we split up that the leg of the side of the triangle that was intersected by that altitude, and we just do some standard right angle trigonometry on one of the triangles. So for example, the cosine of alpha is equal to e, the adjacent side divided by this hypotenuse b, so e over b. If we solve that for e, we get this. If we do the same thing for d, sorry, if we do this over here, we know that because we know what d is equal to, right? It's c minus e, right? So d is the remainder of when you subtract e from the entire side length c. And then if you also you can do sine on this here, and you'll get this side length of b sine alpha for h if you want to find that height. Then you use that height, right? You use the Pythagorean theorem here, and you'll find this. And then we do these substitutions for these different terms for e and h that we got, or sorry, not e and h, d and h that we found, and you end up with this, which is the law of cosines, and all the math is explained right there. And it's really not like that terrible of an equation to use. There's kind of a pattern to it. If you're trying to find a squared, then the only letters you should have over here are b and c. If you're trying to find b, the only letters you should have on the equal side are a and c. So let's look at all three versions of the law of cosines. And these are all the same thing. It just depends on what you're trying to find, right? So if, for example, we're trying to find side length c, then we would go with the one that has solved for c squared. If we're trying to find side length a, we'd go for the one with a squared. If we're trying to find an angle using the law of cosines, then use the one that's trying to find the angle you're trying to find. Use the one that's, has that angle in it. And so we're going to do an example of kind of each of those here. Um, so actually, let's do this problem. So we've got a triangle here, and we're given, notice what we're given. We're given a side, an angle, and a side. So this is classic, this is a classic law of cosines problem here. And we're going to set this up where we want to solve for c first, okay? So we're going to use c squared is equal to a squared plus b squared minus 2ab times the cosine of angle gamma. Okay, so what's angle gamma? Well, angle gamma is a 70-degree angle that's given to us. Okay, so let's just plug these numbers in and see what happens. C squared is equal to a squared, so we'll call this is a, this is b. It doesn't matter which one you call a and b in this particular, well, in any of these cases, because you have addition, which is commutative, and you have multiplication, which is commutative, so it doesn't matter here. But let's just label them the way we have, because a is usually opposite angle alpha and b is usually opposite angle beta. Well, not usually, but kind of always. All right, so plugging numbers in, we have 12 squared plus 5 squared minus 2 times 12 times 5 times the cosine of 70 degrees. And this is going to require a calculator at some point, but we can do a fair amount of this beforehand. 144 plus 25 minus 12 times 5 is 60 times 2 is 120 times the cosine of 70 degrees. C squared is still equal to this. C squared is equal to 144 plus 25 is 169 minus 120 times the cosine of 70 degrees. Now at this point we could factor something out, but why bother? We can just plug this into a calculator, and we're going to have to take the square root at the end of this. So 100 and, oops, sorry. Turn on calculator, there you go. So 169 minus 120 times the cosine of 70 degrees. And this is 127, no, sorry, that's c squared, right? C squared is equal to, this 127 thing ish, right? We need to take the square root of this, so square root of that is equal to 11.31. So C is 11.31. That should make sense based on how we have these angles set up. Well, actually, we don't really know yet because we don't know what the angles are. But just kind of geometrically speaking, it looks like 70 is a little less, and it looks like alpha is a little bit larger than 70 if this was all drawn to scale. So if the side length opposite our larger angle alpha is 12, then the slightly smaller angle of 70 degrees should be a little bit less than that, and it is. So, okay, now at this point, right, we've done the law of cosines. You should only ever have to do the law of cosines once in a problem. The law of cosines is kind of a pain in the butt. So, the law of sines, which is a much more, it's a quicker way of doing things, that's what we should do. Now, we should not use this 11.31 rounded value that we use, because we have a calculator. We're going to need a calculator for every step of this. So, let's say, for example, I want to find alpha now, right? So the sine of alpha is to the side length of 12 as the sine of 70 degrees is to the side length of C that we just found. Now C is not an unknown here, right? We know C. So if we solve this equation for angle alpha, well, sine of alpha is equal to 12 times the sine of 70 degrees divided by C, which again is known. Now if we kind of do this thing here where we take the inverse sine of both sides, or the arc sine of both sides, then then what we're going to end up with is alpha is equal to the inverse sine of 2, no, sorry, is it 2? What's the 2? Oh, 12, sorry, 12 times the sine of 70 degrees divided by C, all inside the parentheses there. So let's do that. We've got C is this answer, right? We're going to keep that in the calculator. So we're going to take the sine inverse sine of 12 times the cosine of, no, times the sine, sorry, sine of 70 degrees, and we're going to divide that by that exact value that we had. Okay, and we're going to get 85.45 degrees. So alpha is 85.4, was it? Sorry, 85.46 degrees. Let's just say 46. Let's round it to 2 decimal places. And now beta, we don't need to use the law of sines to find beta because, again, 180 minus 70 minus, I say minus 70, I wrote plus 70. Minus 70 minus 85.46 is going to give us what beta is. So what is that? 180 minus 70 minus that answer we just got. that means that beta is 24.54 degrees. And that's how you solve that problem, using the law of cosines first, and then go to the law of sines to find an angle, and then just use your property of the triangle to find the last one. And then one more problem here. So this is a situation where we have all the side lengths, but we do not have an angle. So we're going to need to use inverse trig with the law of cosines to find this one. So you can pick an angle. Let's say this one. Let's call this, also this is kind of a non-standard thing. So let's call that alpha. Let's call this beta. Let's call this gamma. It doesn't really matter how you do it. But let's just say we want to solve for alpha first. It really doesn't matter. So the equation that has alpha for law of cosines is a squared is equal to b squared plus c squared minus 2bc times the cosine of angle alpha. And we're going to solve this for alpha. We can do that before even plugging anything in. So we're going to subtract b squared and c squared from both sides. Show that. Minus b squared minus c squared minus b squared minus c squared. Okay, and we're going to end up with a squared minus b squared minus c squared is equal to negative 2bc times the cosine of alpha. Divide both sides by the negative 2bc. Right, now we're going to have cosine of alpha is equal to a squared minus b squared minus c squared divided by negative 2bc. Now we're going to do a similar thing that we did in the previous problem, where we're going to take the inverse cosine of both sides to kind of solve for alpha here. So the equation that we're going to plug our numbers into is going to be this. Alpha is equal to the inverse cosine, or the arc cosine, of a squared minus b squared minus c squared all over negative 2bc. Alright, so let's plug this into a calculator. Oh, actually the values, right? So a squared was 13.9 squared. B was, we're going to call B 10.5 squared. And we're going to call C 6.4 squared. Okay, minus 2 times B, which was 10.5, times C, which was 6.4. Right, type all this in the calculator and we'll get alpha. This is kind of a pain to type in, but it's alright. Second inverse cosine, so second cosine gives me inverse cosine. And now in the denominator, I'm going to put parentheses here. I have 13.9 squared minus 10.5 squared. So that is not saying negative 10.5 squared. Sorry, I can't type 10.5 squared. It's saying minus whatever 10.5 squared is. So that's okay. We don't need extra parentheses there. 6.4 squared, right? Parentheses to close the numerator, divided by negative 2 times 10. Sorry, this needs to be all in parentheses also. Let's do that. So all this is in parentheses. Negative 2 times 10.5. Nope. 10.5 times 6.4. And close the denominator, close the inverse cosine function, and we get 108.2 degrees. So alpha was 108.2, or yeah, 108.2 degrees is what our alpha looks like. So that's cool. Now we can use a law of sines to find beta and gamma, because law of sines again is a lot nicer. But we're going to use this exact value still, not 108.2, but whatever it was when we did our calculator. So let's set up just to find, for example, if we wanted to find beta. So the sine of angle beta is to the side length of 10.5, as the sine of angle alpha, which this is known, okay, is to the side length of 13.9. So once we arrange some stuff, we'll find that beta is equal to the inverse sine of 10.5 times the sine of alpha divided by 13.9. So if we plug that in, we will have the inverse sine, inverse sine of 10.5 sine, 10.5 sine of the answer we just got divided by 13.9, and we get 45.85 degrees. Okay, and then gamma, or what, yeah, gamma. Gamma is going to be 180 minus our 108.2 minus our 45.85, 45.89, right? 45.9. Let's just say let's just keep to one decimal place. And follow your teacher's guidelines about how many decimal places they want uh, in these angles or on the side lengths. So 180 minus 108.2 minus 45.9, and we get 25.9 degrees. So gamma there is 25.9, which all this stuff should make sense. Gamma's C, side length C is the shortest side, so gamma should be the smallest angle. And so there we go. That's using the law of cosines. Again, only use the law of cosines once per problem, then have the law of sines take over. Now, if you've learned this stuff before, you might be noticing that there's an elephant in the room that we have not addressed yet, and that is the case of the angle side triangles, where we are given an angle and two side lengths, and those side lengths are not the two sides adjacent to that angle. So that presents something known as the ambiguous case, and that is the topic of our next video.